This is a video to help you with application problems we did not go over in class today. So this will only last a few minutes, so I'll hurry up. One thing to reiterate that we talked about with inverses today, just be really careful if you have something that's maybe nonsense like this. There's no way that arcsine could be 3, so that would be undefined or no solution. Another thing to think about is if you have like inverse cosine of the cosine of 300, what you would do there, just work it from the inside out. Don't just cancel out these words. You've got to be careful with that you answer correctly. This arc cosine can only be in the first and second quadrant. And so 300, the answer to cosine of 300 is -1/2. And the arc cosine, the cosine of 300 is +1/2, excuse me, because of all students take calculus. So you go looking for an angle in quadrants 1 and 2 that give you a cosine of +1/2, and you would find it right here. All right, moving on to your application problems though. On your application problems, you had one on page 324 about photography, I think, number 100. Number 100, a television camera at ground level is filming the liftoff of a space shuttle. So you have a television camera filming the liftoff of a space shuttle. So as it goes up, this angle changes right here. 750 meters from the launch pad. So you know you're 750 meters away from where it's launching. Let theta be the angle of elevation. Angle of elevation is when you're looking up at something. And let me go in and talk about that. If I'm standing here on the ground and I see like a helicopter or an airplane I'm going to look at that's flying over, my eyes look up at it. So I'm sweeping up my eyes to look at that. That's an angle of elevation. An angle of depression, many people get confused. An angle of depression would be if you're way up high, like on the top of a building, and something's happening below you, like down here, and you hear a lot of activity down on the ground, you're like looking across and your eyes sweep down. That's the angle of depression right here. That's an angle of depression, not this one. Okay, so they're really like this. This is an angle of elevation, sweeping up to look at something. This is an angle of depression, sweeping your eyes down to look at something from up high. So they're kind of like alternate interior angles. So be careful if you're up here and you hear something down here and you're looking down at it. This is not your angle of depression. If you're up here looking at an object, this would be your angle of depression, sweeping your eyes down to look at it. All right, but anyway, back to this problem. So, let theta be the angle of elevation, and let S be the height of the shuttle. So it's going up, up, up. All right, so it said write theta as a function of S. That means you want to solve for theta. So I would say tangent of theta on the A part. Tangent of theta, if I look at, let's say this triangle specifically, we'll just take one of them. Tangent of theta is opposite over adjacent. And so to solve for, this is an S, to solve for theta, I'd say theta is arctangent of S over 750. And then the B part, find theta when S is 400 meters. So I'll find the angle when S is 400 meters. And then I'll find theta when the angle is 1600 meters. And this is where I wanted to make sure we did application problems because it brings up an interesting discussion. When I go to push arctan of this ratio, there's lots of angles that give me a tangent of a positive number, but can you see most likely, and in this case it is the one that I want in the first quadrant, arctan of that angle that I'm looking for is, they asked us I think to do it in radians. And so B, I got 0.49 radians. And then see, I got 1.132 radians. Did they say do it in radians? Anyway, the answer was in radians, but you could also do it in degrees and get degrees. So of course the angle of elevation is going to get bigger as the shuttle goes higher, and you have to look farther up. But that is a kind, like you're actually solving this problem, so you have to take these answers with a bit of doubt. Like, are they really what we need, or do I need to add more to them? But since this is all acute, those are fine answers. All right, the next one is number 102 on that page. Number 102, you have an airplane flies at an altitude of 6 miles above, toward a point directly over an observer. So here's an observer. Here comes the airplane. And so the observer's looking at the airplane as it flies toward them. And so as the airplane flies more toward them, the angle of elevation changes. The only thing that's constant here is how high the plane is flying. It's flying at an altitude of 6. So if we take this right here, you have an altitude of 6. And this is theta, and this is what we're looking for, I think. Write theta as a function of x. So on the A part, I would say tangent of theta is 6 over x. And so then I would say theta can be found by doing arctan of 6 over x with some thought as to if it's the right size of what I want actually after I finish it. And they asked how far away was the plane when theta was 66 degrees. Oh, I'm sorry, I was reading another problem. So the B part is find theta when x is 10 and when x is 3. So I'm going to push arc tangent when x is 10 and arc tangent when x is closer or 3. Let's see what we would expect to happen here. When x is 10 as opposed to when the plane gets closer and x is something smaller like 3, the angle should grow as the plane gets closer. The answers to that, they did it in radians again, is 0.54 radians and 1.11 radians. It'd be interesting to also do it in degrees. It might mean a little bit more to you there since you're more used to degrees. On a test, I would say what mode I want it in. Going to the other application problems on page 333. Number 22. All right, on 22, you have home maintenance. So snow is being thrown from a snow blower with an angle of 66 degrees, angle of elevation, from a chute. So you've got the snow blower with the chute 2 feet off the ground. And is it possible for the snow to clear an 8-foot high fence that is 4 feet from the snow blower? So you don't want to be just like blowing snow and it come down on the same side. You want to blow it like over the fence. And so what I did there was I used tangent of the angle of elevation was 66 degrees. So tangent of 66 degrees. Let me draw it. This is what we need to know. Okay, this is 2 feet off the ground. There's a fence over here that's 8 feet high, but I don't really know how high to draw it in relationship to this right now. The snow blower's at an angle of elevation of 66 degrees, and we know this is 4, so I'm going to find x. So I'm going to say x over 4. I'll put my calculator in degrees and solve for x by multiplying 4 to the other side, and I got 8.984, which is plenty to clear an 8-foot fence, but really it's even more than that because this is the x that we found. And we also have this extra 2 feet. And so we know the snow is going to go 10.984 feet like this, and so it would definitely clear an 8-foot fence. And then problem number 27. On 27, and so you have this parade reminding me of, it looks like a Halloween parade, but kind of reminded me of Macy's Thanksgiving Day Parade. So you've got this balloon. I'm not going to try to draw a witch, but you've got this balloon that you have tethers. Balloon is upright, and the balloon is floating approximately 20 feet above the ground level. And so this is 20 feet above the ground level. You are standing approximately 100 feet from the balloon, but I didn't draw that quite correctly because you are, what they say, I think they said that you're 6 feet tall. And so you're actually like here holding this tether to the balloon. So here's like a person holding the tether. And so the ground's down here. And this was, I think they labeled the person 6. You're 100 feet away from the balloon. And the balloon's 20 feet in the air. So that whole thing's 20. We know this sits, so this would be 14 since this is also 6. And we want the length of the tether. All right, so for the A part, to find the length of the tether, I did the Pythagorean theorem. So oh, and I'm sorry, I didn't answer the whole question. It said on the A part, find an expression for the length L of the tether in terms H, the height of the balloon from the top to the bottom. And so they didn't tell us the height of the balloon from top to bottom. And so this is H right here. Or did they? No, let's see, I had labeled this 14. Hang on, let me read the problem again. I'm sorry. I'm not reading it very carefully. Let me start over. So I'll read every word. Okay, so you have this 6 foot tall person holding a tether. There's a balloon. The balloon is upright and the balloon is floating approximately 20 feet above ground level. So this whole thing is 20. This isn't drawn to scale, but we know this is 6 and this is 14. And this is H, the height of the balloon. And this is, you're standing 100 feet from the balloon. All right, so that's drawn better because I took time to read it. So this is the height of the balloon right here. And so if I'm actually looking at this triangle, then I can do the Pythagorean theorem to find L. I can say 100 squared plus this side squared, which is the height of the balloon, plus this 14 feet, equals L squared. And this is where our square root comes in. So L, if I square root both sides, would be the square root of 100 squared plus H plus 14 squared. And we're supposed to technically think about plus or minus, but this is an actual length of a tether, so we know it's the positive. Let me redo that. Okay, and then the B part. The B part is find an expression for the angle of elevation from you to the top of the balloon. So if I'm going from me to the top of the balloon, this is my angle of elevation right here. And so I want from me to the top of the balloon, and so, I'm sorry, let me read the question again. Find an expression for the angle of elevation theta from you to the top of the balloon. So there's a few trig words you could use here, but I chose to use cosine theta because I thought that was the easiest one, and go adjacent over hypotenuse. You could have used tangent, like tangent is h plus 14 over 100, but this was the easiest one to use if I'm going to use one. And then C, the angle of elevation of the top of the balloon is 35. So now I'm going to find the height. So I'm going to use 35 degrees. I'm going to use this. So I'm going to say cosine of 35 degrees equals 100 over L. When I solved that, I got L was 122.077. So now I know L. And once I know L, then I can find H using this. And so I'm going to go back and say 100 squared plus h plus 14 squared equals 122.077 squared. Solving for h, I have h plus 14 squared equals 122.077 squared minus 100 squared. You found from me this year that I don't punch in a lot of numbers until the end. Then to solve for h, I'm going to square root. I'm going to ignore plus or minus because I know this is a height that's positive. So it's the square root of whatever number this is. And then to solve for h, I'm going to subtract 14. For h, I got 56.021 feet. There's other ways to work the problem as long as you get the answer right. I'm okay, but cosine, oh, that's 56. Cosine, I felt like, was the easiest of the three trig words to use. So you can look around and make your decision as to what makes your life easier when you've got components of a triangle. You want to look and see what the easiest letters are to use in your situation.